After studying this module, you shall be able to know about the requirements of complexometric titrations, know about equivalence point and end point, learn about titration curve, titration error along with derivations for complexometric titration error. Know about metallochromic indicators for complexometric titrations and learn about various numericals dealing with the complexometric titrations. Now let us see what are the requirements for the complexometric titrations. Complexation titration should be stoichiometric so that the basis for the calculation can exist. The rate of complexation should be very fast. The stability constant of the complex should be sufficiently high so that sharp endpoint can be obtained. The complexation reaction should take place in a single step. There should be suitable indicator available for detecting the endpoint during the complexation or the titration. There should be no formation of precipitates or any absorption. Otherwise, there will be an error. All these requirements are generally matched by polyamino carboxylic acids type of complexing agents, for example, EDTA, DCTA and NTA, etc. Now, let us define some terms in connection with complexometric titrations. Take the complexation reaction of the type where metal M reacts with ligand L to form metal-ligand complex represented as Ml. Now, the stability constant Kml can be equated and represented by equation number A as shown on the screen, where it is mathematically is equal to the concentration of Ml divided by the product of the concentration of M, metal and ligand respectively. At the equivalence point, there is no color change, and here at the equivalence point, the concentration of the ligand L is equal to the concentration of metal, and mathematically it is shown as equation number 1, where the concentration of metal at the equivalence point is equal to the ligand concentration at the equivalence point, and Cm, which is the total metal concentration, is equal to the concentration of M plus Ml. Now, further, if the concentration of M is equal to 0, that follows Cm becomes equal to just the concentration of Ml as shown in equation number 2. Therefore, from equation number A, we have Kml is equal to concentration of Ml at equivalence point divided by M concentration at equivalence point into L at the equivalence point. So, Kml, which is the stability constant of metal ligand, is equal to Cm divided by the product of the concentration of M at equivalence point into L at the equivalence point, which is further equated as Cm divided by M square at the equivalence point. Now, this can be rearranged to get the value of M at the equivalence point, which is shown as M equivalence is equal to Cm divided by Kml whole raised to the power half. Now, taking log at the both sides and further taking the negative side signs, we get minus log M at equivalence point is equal to minus half log Cm plus half log Kml. Therefore, since minus log M equivalence is equal to Pm equivalence, so therefore Pm at the equivalence point is equal to half Pcm plus half log Kml. Now, considering this equation in terms of conditional stability and additional stability constants, it can be represented as follows, where it says P dash m at the equivalence point is equal to half inside the bracket PCm plus log K dash ml bracket closed. We can further understand this discussion by taking an example. Calculate the PM equivalence in a titration of a metal ion having the concentration 10 raised to the power minus 13 molar with EDTA at pH is equal to 10 using EBT, which is ediochrome black T, as an indicator. Given that log K metal indicator, now here indicator is EDTA. So, instead of Mi it is log K m EDTA is equal to 18.4. So, Pm at equivalence point, putting down the values, it can be calculated, it is coming out to be 15.7. Now, let us understand what do we understand by titration curve. Titration curve gives information about the inflection point, which is the point at which the color change occurs. The steepness of the point of inflection increases with the increase in the stability constant. It further means that K metal EDTA is directly proportional to the steepness of the graph. The error in the titration is known as titration error. It is mathematically given by this equation, which says that titration error is equal to the difference of the ligand at the end point minus metal at the end point divided by the total metal concentration Cm. Now, let us suppose that the error is plus minus delta Pm. Further, we know that delta Pm is equal to Pm at the end point minus Pm at the equivalence point. Taking log, we say that delta Pm is equal to minus log of metal at the end point plus log of metal at the equivalence point. Taking negative sign, so we have minus delta Pm is equal to log of metal at the end point minus log of metal at the equivalence point. Now, this equation can be rearranged because minus signs are there for log. So, this becomes, after rearrangement, minus delta Pm is equal to log of metal concentration at the end point divided by the metal concentration at the equivalence point. Further, it means 10 raised to the power minus delta Pm is equal to the ratio of the metal ion concentration at end point and equivalence point respectively. So, this can be rearranged where the concentration of the metal ion at the end point becomes equal to 10 raised to the power minus delta Pm multiplied by the concentration of the metal at the equivalence point. Further, at the equivalence point, the concentration of the metal becomes equal to the concentration of the ligand. Now, we can substitute this in the above equation. So, therefore, the ligand concentration at the end point becomes equal to 10 raised to the power minus delta PL multiplied by the concentration of ligand at the equivalence point. Now, considering this general equation where metal and ligand combines to form Ml metal ligand complex, the stability constant of this above equation is given as Kml is equal to concentration of Ml divided by the concentration of metal M multiplied by L. We can take log on both sides and further it is simplified and represented as log Kml is equal to log Ml minus log M minus log L. Since minus log M is Pm and minus log L is PL, so these two can be represented in this equation. So, finally, log Kml becomes log Ml plus Pm plus PL. Now, further, if there is any change in PL value, it can be compensated by Pm or vice versa. Therefore, delta PL is equal to minus delta PM or delta PM is equal to minus delta PL. Equation 4 and equation 3 can be substituted in equation number 1, and the titration error is represented by this equation as shown in the screen. Substitution of equation 4 and 6 and 7 in this equation gives the value of titration error as represented. Now, since metal ion concentration is common, that can be taken outside the bracket, and further it can be simplified, and substituting this value of m by Cm, we finally arrive at the equation number 8 for titration error. Now, this equation number 8 is valid only when delta Pm is greater than or equal to 0.4 and stability constant K is greater than or equal to 10 raised to the power 7. Further, when delta Pm is less than or equal to 0.4. Let us suppose a equation where y is equal to a raised to the power x. So, taking natural log on both sides, ln y is equal to x ln a, which further means that y is equal to exponential x ln a. Similarly, 10 raised to the power delta Pm is equal to exponential delta Pm ln 10, or 10 raised to the power minus delta Pm is equal to exponential minus delta Pm ln 10. Now, we know the general equations for exponential x and exponential minus x. Exponential x is 1 plus x square by 2 factorial plus x cube by 3 factorial plus so on, and similarly exponential minus x is 1 minus x plus x square by 2 factorial minus x cube by 3 factorial and so on. Similarly, using the above two formulas, exponential delta Pm ln 10 becomes equal to 1 plus delta Pm ln 10 plus delta Pm ln 10 whole square divided by 2 factorial plus so on. Similarly, exponential minus delta Pm ln 10 is equal to 1 minus delta Pm ln 10 plus delta Pm ln 10 whole square divided by 2 factorial plus so on. Subtracting these two terms, 10 raised to the power delta Pm minus 10 raised to the power minus delta Pm becomes equal to 2 delta Pm ln 10. Transforming it, changing it from the natural log and putting it and multiplying it by 2.303, it becomes nearly equal to 4.606 delta Pm. By putting this value in the above equation number 8, the titration error is equal to 4.6 delta Pm divided by under root Cm into Kml. Let us take one example. Calculate the titration error or the indicator error in the titration of metal having concentration 10 raised to the power minus 3 molar with EDTA at pH is equal to 10 using EBT as an indicator, given that Pm at the end point is equal to 5.9 and log Kml is equal to 8.4. Now, we know the equation which says that Pm at the equivalence point is equal to half Pcm plus half log Kml. So, we can substitute the value of Pcm and the value of Kml, and on substituting and calculating we get the value of Pm at equivalence point as 5.7. Further, delta Pm is equal to Pm at the end point minus Pm at the equivalence point. So, on subtracting these two terms, delta Pm is equal to 0.2, and we can substitute these values in the equation for the titration error, and on substituting it we get the final answer of titration error as 1.83 into 10 raised to the power minus 3 as answer. Let us now derive the expression for the titration error. We know the titration error can be represented as shown: Cl minus Cm divided by Cm, where Cl is the concentration of the ligand and Cm is the concentration of the metal. Further, we know Cm is equal to m dash concentration plus ml concentration, and Cl is equal to L dash plus ml. Considering this equation where m dash plus L dash combines to form metal-ligand complex, now here the stability constant represented as K dash 2 is equal to the concentration of ml divided by the product of the concentration of m dash and L dash respectively. Rearranging the above equation, the metal ligand ml concentration is equal to K dash multiplied by m dash and L dash. Further, Cm minus m dash is equal to K dash, m dash and L dash. So, this equation can be, on rearranging, we get the value of concentration of L dash as Cm minus the concentration of m dash divided by K dash into m dash concentration. Therefore, the titration error is given as L dash concentration minus m dash concentration divided by Cm. Since Cm is common in the denominator, in the next step we can show it separately with the numerator. So, this shows that L dash concentration divided by Cm minus m dash concentration divided by Cm. Now, we can substitute the value of L dash concentration calculated above in this equation, and on substitution we get the answer of titration error at this stage as Cm minus m dash concentration divided by Cm K dash m dash concentration minus the concentration of m dash divided by Cm. If Cm, which is the concentration of metal ion, is far greater than m dash concentration, so under this condition the numerator, which is Cm minus m dash, can be simply substituted as Cm only. So, thus the titration error becomes equal to Cm divided by Cm K dash into m dash concentration minus m dash concentration divided by Cm. We can cancel the common Cm terms from the numerator and denominator, and this equation can be simplified and is represented as shown: titration error is equal to Cm minus K dash m dash concentration square divided by Cm K dash and the concentration of m dash. Now, this equation is valid only if the stability constant K is less than 10 raised to the power 7. Considering now the equation where metal combines with an indicator, metal M combines with indicator I to form a complex metal indicator abbreviated as Mi. So, calculating the stability constant for Mi, It is shown over here. Kmi is equal to concentration of Mi divided by product of concentration of metal M and indicator I, or it can be further equated and represented as 1 upon concentration of metal minus concentration of metal indicator divided by concentration of indicator. Taking log on both sides, the equation becomes log Kmi is equal to minus log metal concentration plus log of metal indicator concentration divided by the concentration of the indicator. Now, from the conditional constants, we know that K dash m is equal to Kmi divided by alpha m and alpha I, or taking log on both sides, this becomes log K dash m is equal to log Kmi minus log alpha m minus log alpha 1. Further, at the end point, the metal indicator concentration Mi is equal to I dash concentration. So, substituting this, we get Pm dash transition is equal to log K dash Mi minus log of Mi minus log of alpha m. Let us study what are the requirements of metallochromic indicator. The color reaction should be highly sensitive, so that at the end point, even when very small amount of metal ions are present, the solution is highly colored. Every indicator should be highly specific or selective, just like murixide, which gives color with nickel. The metal indicator and the indicator color should be very different. There should be a vast contrast between the color. The stability constant should be sufficiently high, so that during the titration no dissociation can occur. The rate of the reaction of EDTA, ethylene diamine tetraacetic acid, with metal indicator complex should be very fast, so that the end point should be very sharp. The stability constant of the metal indicator Kmi should be less than the stability constant of metal EDTA, so that at the end point the metal indicator can be easily displaced by EDTA. The color change of the indicator must be at the end point of the inflection of the titration curve. Let us do some numericals. Now, taking this example, calculate the maximum titration error when magnesium Mg, when magnesium having the concentrations 10 raised to the power minus 2 molar and 10 raised to the power minus 4 molar is titrated with EDTA at pH is equal to 10 using EBT as indicator. Given that P magnesium transition is equal to 5.4 plus minus 0.5. To what color change the titration should be performed? Given that log K of magnesium is equal to 8.2 and pH is given just like above is equal to 10. So, we can substitute the values to calculate P of magnesium transition, because P magnesium transition is 5.4 plus minus 0.5. So, first adding 0.5 and in the second step subtracting 0.5. So, we have got two values of P magnesium transition as 5.9 and P magnesium transition as 4.9. Now, using the general equation or formula for Pm equivalence point, just substituting the values and calculating Pm at equivalence point comes out to be 5.1. Now, this can be represented or tabulated in the form of a table, where for the concentration 10 raised to the power minus 2, the two values of Pm transition are given. Similarly, Pm equivalence two values are there, 5.1, 5.1. Delta Pm is calculated. Km, Cm raised to the power half, these two values are calculated, and when we substitute these values, the titration error at the concentration 10 raised to the power minus 2 comes out to be minus 0.073. Now, for the other concentration 10 raised to the power minus 4, similarly it can be tabulated. Two different values of Pm transition. We have calculated the value of Pm at the equivalence point as 6.1. Delta Pm is calculated at two different values of Pm transition as minus 1.2 and minus 0.2. So, Km, Cm under root values are calculated as minus 10 and minus 0.7. So, similarly, just like above, it can be calculated for 10 raised to the power minus 4. We can find the titration error for delta Pm greater than 0.4 by putting the values in the equation as shown. If Pm transition is higher than Pm equivalence point, we get a blue color. But if P metal transition is lower than Pm at the equivalence point, we get reddish blue color. For example, at the protonation constants for various metallochromic indicators are given in the table, abbreviated as A, B, R, T. Different values of log beta 1, log beta 2 and log K magnesium are given. Which of these indicator is most effective to magnesium at pH is equal to 10? List the other indicator in order of decreasing sensitivity to magnesium in complete. Complete the solution or simply the question is asked. Now, the order of indicators in